Let's have a look at a slightly harder example now. This one's a bit more tricky because it's got pronumerals on both sides and one of them is also in the denominator. So the hack that we've already seen is that we can get around this problem by multiplying both sides by the square of the denominator. That way we know that we're multiplying by a positive number and we know that we won't need to flip the sign. I'm going to show you a couple of methods for solving this same problem, just so that you've got a few different tools, I guess, in your toolkit. Because each problem might sort of present itself with a different method that appeals to you. Now, the first thing that really makes sense to me is to look out for potential problems. Straight away, I can see that x can't be equal to 2, because if it is, we've got 0 on a denominator, and we can't have that. So I'll write that down before I get started. Using a different colour actually just reminds me to look out for that at the end, because that's a consideration that I could forget about later. Now I'm going to multiply both sides by the square of the denominator. Now, if you like to show every single line of working so that you don't get confused, you can go ahead and write that line. I can in my head think through that when I multiply by the square of this, then one of these is going to cancel with that one on the bottom. So I'm literally just going to generally start these ones by doing that part in my head and cutting to this. But if you like to do that in between line, that's perfectly fine. Now I need to multiply the other side also by that square of the denominator. So both sides have had the same treatment. Now I need to get everything on one side. So you can subtract this from both sides or subtract that from both sides. Take your pick. I'm going to leave nothing on the left-hand side, and I'm going to subtract, whoops, that's not x squared, x minus 2 all squared. I'm going to subtract 3 lots of x minus 2 from both sides. Now, remember, we don't want to expand this out, because if we do, we get something that's much nastier looking. Actually, we want to keep it factorised, and we want to factorise it even better if that's possible. So I can see here that both of these terms have got x minus 2 in them. So if I bring that out the front and use square brackets to now factorise each of these two parts, I can see that this multiplied by x and another x minus 2 will give me this first term. And to get this second term, I need to do this multiplied by minus 3. Now tidying up the square brackets, again, you could perhaps do that part in your head. I prefer just to write it out so I don't make a mistake. I've got x squared minus 2x minus 3. Now, can I factorise even further? Yep, this looks like it can be factorised, so just keep on going until it's as good as it can get. And I've got x, what's that, plus 1 and x minus 3. Okay, now this is looking pretty good. Now I can see it's a cubic curve. I could tell that it was a cubic curve probably back here, but it's much more obvious now because I can see that this will multiply out to make x times x times x. So let's use that strategy of saying let's graph y equals 0 and let's graph y equals all of this. So then I can see where my cubic curve is going to sit above the line y equals 0. That's a strategy we've used a bit already. Now your sketch doesn't need to be amazing, just a rough sketch is good enough. I can see that I've got intercepts here at -1 and at 2 and at 3 because those are the values of x that would make y equal to 0. So then I can just rough in, a basic cubic curve that goes from low to high and goes through those 3 points. Now I'm looking for where my cubic curve is above or sitting higher than or has a greater value than the line y equals 0. And the line y equals 0 is just the x-axis. So I can see that it's above the x-axis here in these values of x and up here. Okay, I'm making a bit of a mess, but you can see what I'm doing. I want the values between -1 and 2 and the values of x that are greater than 3. So how do I write that? Well, I need x to sit between -1 and 2 or be greater than 3. Now, looking back here, you can see that all the way down I've used this less than or equals sign. So I can see that I need to put some things in here, but be careful. It might be tempting just to whack them all in. But what did we consider at the very beginning? X can't actually equal 2. So that means we don't want that equal sign here because x can be anything between -1 and 2, but not actually be 2. And then it can also be anything greater than 3. So you can now check that this works by subbing in any number that falls in these ranges. X being 4 would fit the bill. 3 over 4 minus 2, that's 3 over 2, that's 1.5. Is that less than 4? Yeah, sure is. What about a number like x being 0? Well, that would give us 3 over -2, So that's minus 1.5. And is that less than 0? Sure is. So quick inspection tells you that both of these domains look pretty good for x. Now the advantage of this method, as I see it, is that multiplying by the square of the denominator is something that we've already learned how to do. So that's quite straightforward. Graphing a cubic curve is easy, and that, again, something that we've already learned. So this method to me looks quite straightforward. The one thing that I'd be careful about is spotting that. If you forget to do it, you might get to the end and put that little equal sign there, and then you'd lose a mark. So putting that in a different color or something and just referring back to it, when you get to the end, look back at your working and you go, oh, don't forget about this. That's the only thing I'd recommend. Be really cautious about that part. Let's look at another method now. What if, instead of multiplying by the square of the denominator, we just started by saying, let's graph y equals all of this and y equals all of that, and see where this graph is sitting below this graph. Now, this method I think is quite good because I can see that this is going to be a hyperbola, and we've already seen in our work on functions how to graph a hyperbola. We can even look at the transformation that's happened to shift it 2 units across. And then this is just the line y equals x. So both of these graphs are things that I can draw quite easily. So let's do a rough sketch. I've got my y equals x there. That's easy to draw. And then this is a hyperbola. Now the 3 will just change how fat and skinny it is. Remember, a basic hyperbola has this sort of shape, and it's got asymptotes on the x and the y axis. And that 3 will just change how wide that sort of waist is, I suppose you'd call it, of the hyperbola. This x minus 2, though, what does that do? It's going to shift the hyperbola across 2 units. Which way? Left or right? X minus 2 moves it towards the positive numbers, actually, doesn't it? So that means it's going to move it over here so that the asymptote will actually be at 2, and it's going to move it across. So it's going to sit something like this. So if I draw this in, I can sketch my x equals 2 asymptote here. The other asymptote will go along like that. And then it's sort of just got that basic shape of the 2 arms, doesn't it? Which I can draw in here, making the 2 arms fit sort of around those crosshairs like that. Now, this is a good enough sketch to sort of tell me what's happening here. Now, which sections do I want? Well, I want to find where my hyperbola is sitting below my line y equals x. So let's use another colour to just highlight where that's happening. It's happening here and onwards forever. And it's also happening here. Okay, so in this section I can see that the line is above and the hyperbola is below. Up here, the hyperbola is actually above the line, isn't it? So I don't want that part. I just want from here onwards. And here I want from this part down towards this. All right, so clearly we need to work out what this point is and what this point is. We already know what this is. It's x equals 2. So how are we going to solve those points? Well, we've got the graph y equals 3 over x minus 2 and the graph y equals x. How do you tell where 2 graphs meet? Solve the equations simultaneously. So if y equals this and y also equals that, then this and that must equal each other. So I can literally solve this now, which is much easier to solve than with the inequality sign in it. So now I can just basically multiply both sides by x minus 2. So I've got x minus 2, and here I can say that's x squared minus 2x, and now I can get everything onto one side. So I've got x squared minus 2x minus 3. Factorising, I get 0 is equal to, what have we got? X plus 1 and x minus 3. So therefore x must be negative 1 or 3. So that tells me that this point here must be 3. That makes sense because it's a little bit to the right of 2. And this point over here must be negative 1. So what are the parts of the graph that I'm interested in? Well, I want this part here from when x is negative 1 all the way up to that asymptote. Now the asymptote is a great way of highlighting to me that I don't want the value x equals 2, because my graph never actually reaches the asymptote, does it? But I can have this point here where x is minus 1. So x has to sit between 2 and minus 1, and it can equal the minus 1, but it can't ever meet the 2. Or I want this section of the graph here where x is 3 or upwards, and it can be 3. So I've reached the same conclusion. I've got the exact same answer as how I did it before. Was it harder or easier? Well, that depends on how good you are at graphing. So the better you get at graphing hyperbolas, say, that have been shifted across 2 units, the easier this method might seem to you. So hold this one in your mind, even if for now you're not a big fan of it, because when you're good at graphing, this one might actually be easier. I think that really the algebra that we had to do was probably simpler in this method than it was in the first method. And the other thing I liked about this method was this asymptote here. I'm quite a visual sort of person, and I guess I can see that my graph never is going to meet that point. And so that makes it much less likely that I'm going to make a mistake and put an equal sign here. I can see that it can't equal it. It's sort of shouting out at me. Whereas I find with that other method, I might sort of forget about x not being allowed to be 2 and maybe put an equal sign in there. So I think this method definitely has some merit.